verifying that arrival process is stationary and inter-arrival times are exponentially distributed. If we want to analyze a process for data that we collected based on some real-life case, we might have arrival data, and we might want to make sure that we have a stationary process and that we have exponential inter-arrival times. So how can we do this? First, a stationary process. Suppose our arrival times are called 81, 82, up to some 80n for n customers. And suppose, of course, they are sorted, increasing. We can plot a graph with 80i on the x-axis, so the time of arrival on x, and then number of customer on the y-axis, and then we can see if they form a straight line, and if the points that we plot form roughly a straight line, then the process is stationary. But in this example, for example, in this picture, you see that the line actually goes, deviates significantly from the straight line, and so this process seems to have some seasonality. And then, if you want to, let me actually show you an example of this. So I have here a data for two processes, right? So this is like two cases, process 1 arrival times and process 2 arrival times. And the question is, are these arrival times stationary? So I'm going to just copy the data for the first process, and I'm going to calculate I over n, or I, this is enough to put I, right? This is going to be 1, 2, and so on. And now I will, right, I have it to the end. There is actually a total of 200 customers here. So if I now select this and create a scatter chart, insert a scatter chart perhaps as a line, you will see that I have something that is actually quite close to a straight line, right? And I can verify this by plotting a line. So I go to insert, and then I just plot a line manually. Like you can see that the line I'm plotting is very close to the chart that I drew. So this first process seems to be stationary. Let me now go back and do the same analysis for the second process. Actually, I will duplicate this, move the copy to the end, create a copy, and then, right, this is going to be process 2. So I'm just going to copy the data in place of the first process. And look what happens. In this case, I have the straight line, right? That is somewhere like this. But the data, which is the blue line, highly deviate from the straight line. So what I see here is actually, in fact, initially the arrival process is much slower, and then it suddenly picks up, especially close to the end of the time period, to the end of the 2 hours, 120 minutes that I'm observing. There is a much higher arrival rate. So I would have to somehow divide this into subsegments. Maybe the first 90 minutes would be one segment, and then another, I don't know, maybe of the remaining 30 minutes, maybe 20 minutes, another segment, and so on. This, of course, is subjective, but clearly process 2, for the 2 hours that I'm observing, is not stationary. The second question we want to answer is, if the process is stationary, are the interarrival times exponential, which would mean also that the arrival process is Poisson. To find if the interarrivals are exponential, we first have to calculate the interarrival times. And remember, interarrival times are just difference, right, between consecutive arrival times. So first we need to calculate them. Then what we need to do is sort them from the smallest to the largest, the calculated values. So we call them some A1 up to AN. Well, if there is 200 customers, we'll have 199 of those interarrival times. And then what we will do is we plot empirical distribution with interarrival time on the x-axis and on the vertical axis, we will have I over n, where I is the index of my interarrival time, right? So I will create a kind of empirical distribution function. The blue points here are empirical distribution function of the interarrival times. And then what I can do is I can plot the theoretical distribution function and see if they do, those two fit with each other. So let me again show you this on the example. So I had two processes, and I established that the first one is stationary, but the second one is not. So the second one requires further a manipulation, dividing into sub segments, into smaller intervals. This is not what I'm going to do. I'm going to focus on the first process now, and I would like to try to see, right, if this is exponential. So remember, this was process one, and just analysis if it is stationary. Now I would like to see if this process is exponential, or the interarrival times are exponential. So to calculate interarrival times, also in minutes, I'm going to take a difference between this second and the first. Then I'm going to create a copy of this. And notice the last one I must delete, because the last one is incorrectly calculated. Right? There is no last interarrival time. Now what I will do is I will take those interarrival times, copy them, and I will paste them as values. In order for me to be able to sort them, I have to have them as values, not as calculated. Notice this is B4 minus B3, and this is just a value 0.94, right? Now that I have this, I can actually take those and I can sort them, right? I will sort them from the smallest to the largest. So now that I sorted them from the smallest to the largest, the next thing I want to do is I want to calculate value I first. This will be 1, 2, and so on. And then I will see the total is 199. So I'm going to, maybe I'm going to insert a column to have them next to each other. I over n will be this value divided by 199. You could automate it, right? So these are the values. And the last thing I need to do is so this is my empirical distribution that I have now, but I also want to calculate what would be the theoretical distribution. So again, I will insert a column here for the theoretical distribution, just to have these three columns next to each other for easier plotting. And I will say this is the calculated or theoretical distribution. And this should follow the exponential distribution function, which, right, has the density is 1 minus exponent of minus this value divided by some average. And this average I will define maybe in this place. And this average actually, which is average interarrival time, I can calculate as the average of my theoretical, experimental values of interarrival times. So this is calculated as average of all those. It is almost 0.6 minutes. And so now I put actually a reference here with dollars to always refer to this, but here to refer to the x value, the interarrival time value for this. So this is my average interarrival here. And so if I copy this, right, so again, I have this to the end of the table. And now if I plot those three columns, I will again insert a scatter chart with lines, and I will show you that, right, there are two lines here. The blue one is for the experimental, right, the empirical distribution, and the red one is what I calculated as theoretical distribution. And I hope you can clearly see that there is a very good fit between those two functions. So I can actually say that process one is not only stationary, but also that interarrival times are exponential, and at the same time, I can say that arrival process is Poisson, or number of arrivals per unit of time will have Poisson distribution. All the best case conditions are satisfied. For those, in this situation, all the models will work most accurately.